Hi everyone. Let's wait for 2 more minutes to others to join, then we can start on today's workshop. We can start now. Good evening, everyone. So myself, Sai Krishna. So I'm working as a technical manager in Intel and having a 13 plus experience in VLSI. And currently, I'm working as a VLSI CAD architect in design and methodologies for cadence related flows with Intel. And despite of having this work experience, I'm currently pursuing PhD from IIT Kharagpur in VLSI, and I'm holding a 12 patents in VLSI related to the low power design techniques. Okay, so my interest into electronics was started back then in 2011 and 2011, and all this were meant to make me realize the VLSS is like a complete a day with a debug and a analyzer, right? So all these are like a completely different world. Okay, yeah, let's start on today's workshop. So in this class, in this workshop, we are learning about complete how the evolution of VLSI. Basically, what is VLSI? So VLSI, where it is using currently. So anyone know like what is VLSI basically, right? Anyone know like what is VLSI and where it is like currently used in our current world, in current work life or ecosystems everywhere, like where you use the VLSI. So you see, right, everywhere you see, everywhere, the smartphones, laptop, EV machines, I mean, smartwatches, smart TVs, medical devices, anything you see that has a microchip or a ICs, okay? That ICs basically, that ICs are basically are the microchips, okay? Everywhere you see mobile process, we call it a Qualcomm Snapdragon process, MediaTek process, the mobile phones and laptop, we see the Intel Core process, AMD process, all these are VLSI things. All these are like very large scale integration. VLSI is very large scale integration. So when it called as a very large scale integration, what it is? So combining a lot of transistors, millions and billions of transistors into single chip that is in a 1 centimeter length. You know, right? 1 centimeter length. The 1 centimeter length, we are packing all these transistors logically to one single chip. One single chip that forms, say, a SOC, what we call SOC, system on chip. So this system on chip will drive complete logic. It will be using for the mobiles, laptops, or anything that you use, monitors, anywhere you see, right? So this will combinedly form a single chip, and we will be using in our daily lives. But how it is constructed, basically, how the this chip is manufactured, and what is the workflow for this VLSI, right? We will go through that, and we'll also go through how the VLSI makes the chip from start to end. I need a chip today. What to do now? So tomorrow we need a complete to drive some application. We need a chip, right? If you need a washing machine with automation, like it will wash automatically. You need a robot or a automatic car. The Tesla cars we see that require a special chip that will control all the hardware parts, the input and output parts, sensors, everything that controls that is a special chip. So all these are the special use application specific integrated circuits, what you say. So all these chips are manufactured in a VLSI flow model only. Okay. Coming to the today's workshop, we'll be learning about VLSI basics, how the VLSI, what are the basic things required in the VLSI, and VLSI design flow. What is this VLSI design flow? And what we call front end, and what is back end. People call someone, I wanted to go back end, and someone called it as a back end. I'm not interested for back end. I'm only interested for front end. But we will confuse what is there in the back end, what is there in the front end. Overall, like what is front end and back end, and what is the fabrication techniques, like how the chip is manufactured and where it is manufactured currently, which are countries serving this, and packing. The chip is can't barely that we like we can put on the motherboard, right? It need a proper graphite carbon packing, which will serve the heat, and it will need a proper packing that will have a good life, right? So that is also packing. And next we'll go over the global semiconductor carriers and India semiconductor field in next 5 years or 3 years, how it will be there, how much the scope for the VLSI engineers currently. Okay. Yeah. Coming to VLSI basics. So VLSI is process of creating a billions and millions of transistors with a single chip. Okay. What is transistor? Someone will get a doubt of what is transistor, right? Okay. What is transistor? Transistor is a switch, electronic switch. A switch is like, what is the switch functionality? What is the switch functionality? 0 or a 1, whether it will off or a on, right? So in the on and off functionality, we are playing with all the logic required. So the transistor, what is the basic transistor? We call it as a basic transistor is a CMOS transistor. Okay, this CMOS transistor having a functionality of NOT gate. Okay, so NOT gate is like when you give a input of 0, it will give a output of 1. So it work when you on the switch will off, the output will be 0 if you give a 1, if you give a 0 it will be 1. So this functionality, with this functionality we are creating a different types of logic gates. right? These logic gates we are used to create all the logic we are required for the particular design. Okay, we'll go to deeper into the each of the thing what we will do for a chip. Okay, so all you see right here the microchips of the different sizes, different functionalities for a one of the FPGAs. Okay, okay. So now how the CMOS is constructed or a made for a creating a full processor or a CPU or a microprocessor or microcontroller. Okay, first we created a CMOS. In order how the CMOS construction was started, combination of PMOS and NMOS. It has a functionality that of CMOS, that is a not gate basically. Okay, by this not gate we have created a basic logic gates for a representation or kind of a logic creation. Any language, if you take a I wanted to speak in some language, especially I wanted to speak in some languages like in Chinese, so I have to be a medium, right, to create some. For that, the same thing for the VLSI, we have a basic logic gate to create these functionalities. Okay, different logic gates will have a different logic behavior, and we are creating a logic for it. Let's take you have adder, basically a adder. If you give input of 1 1, okay, you have a what do you say, you have a adder. Okay, that adder has a uh, functionality of when you give a input of 1 and 1, okay, it will give a output of 1. So how it is constructed then? It using a basic logic gate style. Okay, so with that adder we are creating a combinational logic. Okay, with that combinational logic we were with that, that is not only enough for us, we wanted to store the data. If I wanted to store the data, especially I wanted to store that one data which is same, a user has a 1 1 input and output is 2, that is like 1 0. I wanted to store this data that required a flip-flops or a register. That is how the sequential logics are created with input of clocks, right? So with this logic we are creating a flip-flops to store 1 bit of data. Okay, 1 bit of data. And with the 1 bit of data it can store only one, either 1 or a 0. If you wanted to store a multiple bits, like I wanted to store a number like 1011, to store that data we need how many flops? Basically we need 4 flops with a counter added, right? With that it will create some logic, it's a number. So that's where the ALUs, control unit and program counters are came. Okay, then store the maximum data like in a complete memory structured way. We are creating a memories, interfaces, buses. And if you wanted to add some inputs and outputs for a particular logic, if you wanted to add some USB where you wanted to control the light or some kind of fan or kind of a what do you say, a mouse, okay, or a Bluetooth or a Wi-Fi. So we need input and output interfaces for that. With a combination of all these things, we are creating a full processor that is a CPU. Okay, but one other thing here, you can't create directly here the NOT gate directly can't create the full processor here, right? It has to be again converted into a CMOS, AND gate or OR gate or a NOR gate or NAND gate. So how that again deployed that NOT gate or AND gate it is CMOS, again it is physically implemented on a wafer or on a silicon bar. Okay. Yeah, next one. So regarding the transistor evaluation, sorry. So this is like from the small scale to how the large scale currently. So previously in the back then, creating a one transistor is like a one two, like it's like a big data, like there has to store the switch, right? So it is like a complete a big equipment for them. But currently we are storing a 2 billion, like more than a 2 billion to 10 billion of transistors into a single chip. That is the size of just a small 1 centimeter long, 1 centimeter into 1 centimeter. So how this evolution was come up? And this is like decreasing the transistor size and consuming the each transistor with a low and very low powers. Okay, so it was becoming so much of complexity into day-to-day life if you are using equipment. Each and every gadget we are using electronic gadget as a macro processor or any kind of IC we can say. Okay, this is how the evolution. Previously, it was in a glass tubes and it was converted into uh, some kind of a boxes, and then again it was becoming into a chips, and it was into small scale. Again, it was becoming nanometers. So currently, it was CMOS was then again converted to the FinFET, is the latest technologies, and again this FinFET was now evolved to a gate all around transistors. So all are like advanced for the low power usage and the size of the transistors. Okay, and this is a transistor valuation. Like this is like one from the starting from 1970s, the number of transistors growing rapidly. Okay, so here you can see right every year the transistor numbers are doubling. So that is how we call it the Moore's law. Okay, someone is texting this. Let we can take a questions in the later. Okay, yeah, thanks for asking. We can take the questions in sometime the last. Yeah, yeah. So yeah, this is like how every year the transistor, for every 2 years the transistor numbers are doubling. So current trend is at 10 billion. For a normal laptop, it will have at least a 10 billion transistors, I can see. Okay. Yeah, coming to the what is VLSI. This is about the VLSI basics. What is VLSI, like what in terms of what is we can consider as a VLSI basics. And this is the VLSI design flow. So what is VLSI design flow? So you wanted to start chip, right? So I need a chip. So tomorrow I wanted to handle a chip with some 1 TB of data, because tomorrow my quality of image is increasing, my processing of app will increase, and to download a one app I required a at least a 20 at least a 2 GB of data. For that, to handle that, if you wanted to install a 10 apps like that, to handle that you need a RAM of at least a 128 GB in the mobile itself. You will confuse what is about 128 GB RAM, but it will be normal in next 1 2 years. You can still see, right? 16 GB became very normal now, right? So tomorrow 128 becomes very normal. Current laptops are using at least a 80 GB or a 64 GB of RAM. Okay, so this has become very normal. For that, we need a specifications that will work for the chip to handle, right? So that is how the design we have to specify whether uh, what kind of specification, to what speed the chip is required to be worked on. So that is like we are deciding some specification by the vendor. Let's take a app. Let is a HP. My laptop is HP. Let's take. I need a specification that will work very fast, and that will be given to the foundries or a companies like Intel, Nvidia, or you can say AMD. So this will handle the laptop chips that will give you specifications required for them. Okay, so at least this chip will take at least 3 to 4 years to complete from design specification till the production. Okay, so once you decide a chip for a laptop or a mobile, it will take for laptop it will take at least 4 years. For a mobile, it will take at least 2.5 years. So every year the pipeline will be addressed like for the next years. Okay, so going to the VLSI design flow, first we'll specify the design, what is the requirements of the design for a particular chip. Then we'll create a RTL coding. Basically the RTL coding is like you are creating a the logic, particularly the logic. Then that logic will be converted into a Verilog code, and the Verilog code will be functionally verified by the design verification or functional verification team. Okay, then that logic will be resynthesized. Let's take your has some 2 billion gates, but it's not required 2 billion. If you synthesize it properly, if you convert that completely with synthesizing the properly, it will only address only 0.5 billion only. You are reducing 1 by 4th of the complete chip gate, I mean the usage of gates that will perform same activity that performed with 2 billion. So like this will logically synthesis the data. Then the synthesis data will be taken into physical design stage. In the physical design stage, we will be deploying all this Verilog code into real-time layout format in a CMOS. Okay, after this we'll be properly placing the all the transistors in a fashion of without any shorts, without any fabrication issues, and then we are taking into a fabrication for the chip to tape out, and we'll be packing the chip and we're taking into testing and production. Okay, this is how the VLSI design flow. I'll go to each of the topic in detail and we'll cover up what actually the each engineer will do or each flow will do. Okay. Okay, coming to the specifications of the each application. You want some laptop, basically a laptop or a car which having the specific chip. You have to specify how much speed the chip has to work. It has to take a decision in a 0.1 second with at least 1,000 instructions per second. At that speed it has to work. To work that is a speed we have to decide for that chip. And the power consumption. It has to use the less power, right, at the same time. Right? If not, your battery life will die just in half an hour or 1 hour. Okay. The current, if you see, right, the back then the Apple or the iPhones, you see, right, the power consumption was very huge and they were decreased drastically very low because they are using ultra low power cells, ultra low power CMOS techniques, and they are using like the phone itself in a lightweight with a low power consumption of chip with a no heat area. Basically, if the area is more of the chip, even if the 0.1 centimeter is increasing, the power consumption will be more. Okay, so like that, there are a lot of specifications that are required for a chip to design. Okay, coming to the VLSI design flow. So first, we will be having some idea what is the requirement. For what requirement we have to decide. Then we have to specify the specifications required for the chip, whether the chip has to work for 2 gigahertz or 3 gigahertz, and how much power it has consumed, whether the power has to consume a 0.1 voltage, volts per second or like that amperes. We have to decide that how much power has to consume. Then the design architect will design accordingly that chip. So it takes at least 1.5 years to team to decide how the architecture has to design properly. It has to work with this specification. Okay, then RTL team will code the required logic in RTL code format. Okay, once it is coded, the functional verification team will properly validate and verify the code without any bugs and functional failures. Code is 100% working up to mark, then they'll take it to the front, or else there will be again to and fro with the RTL codes to functionally verify that code. Okay. Next, coming to the logic synthesis stage, where there, as I discussed in the last slide, right, we having a millions of transistors, but we don't require all these transistors. There will be redundancy of transistors always. Okay, you can serve one NOT gate will serve a multiple logic at the same time, right? So we have to make logically synthesis this data. Okay, then this will be physically deployed. Like if you see, right, it will physically implement in a CMOS format. Example, the RAMs or anything that is required, we have to physically place them in a, and this is a layout format. Until that, we'll be seeing only the coding part here, the codes of Verilog code, what you say, and it can't be directly we can see. Okay, then it is taken into fabrication for the manufacturing of these chips. So one signal chip may have the one signal wafer may have a multiple chips, and that will be diced again. I'll discuss about this each of the step. Okay. Yeah, this is about the specifications. Like this is the example that I need a 6 cores with 6 threads, and the previous my was just working for 2 gigahertz. But I wanted to work for at least 4 gigahertz. Okay, this is how we are specifying the design specification for the architectural designers. Okay, the architectural designers are very experienced in designing this. Okay, in terms of the design of these chips. Okay, when the architecture is designed, the requirements of the specifications are provided with the speed, functionality, physical dimensions they will specify. Okay, and what is the design technique to be used, whether that is our application specific or FPGA or SOC system on chips. Someone is asking like SOC, what is SOC? Then I just said, right, so combination of multiple features into single chip basically. Okay, fabrication technologies. Someone say like, what is technology then? Technology is thinking day to day. So it's running at 2 nm. And this is like we back then started with 180 nanometers in 10 years back. That is the size of transistor of the channel length, and this is the nanometer. It is decreasing. The size of the transistor is also decreasing day to day. The current trend we are using in our mobiles are 7 nm, and the laptops are having 10 nm. And 5 nm we see in some of our iPhones or some of our latest mobile processors, and 2nm is in the market in next 6 months, and that is manufactured by Intel and TSMC. Okay, so these are the main that fabrication technologies matters when you choose your VLSI. So this complexity will increase. If you are designing a chip, this size is decreasing, then your gate count, your transistor numbers are doubling. Okay, and what is this trade-off between the market requirements and the technology, that country requirement time, all these are dependent upon the specifications requirement for the chip to design. Okay, coming to the RTL design and synthesis. So RTL will also design the code and the resynthesis properly, and this code will be transferred to the next level. At transistor level, the transfer level, we will be coding in HTL code, that logic and the data of the circuit. So we'll be having some flip-flop like this. That will not be the same. You can't take this into a complete gate level, right? So it will be implemented in a gate level like this. Okay. And this gate level will be, it's not required that this much of logic is required for a flop, right? You can say you can resynthesis it properly with at least a 5 to 6, 7 gates only, using a 1 NOT gate and a 3 AND gates with a Boolean algebra expressions. Okay, so all these are will be involved to make the resynthesis the data to use the lesser gates with a better logic and lesser power. Okay. Now regarding the next step is that when the synthesis test done, RTL synthesis test done, we have to take the whether that logic is functionally working properly. If not, your chip is completely failure. Even out of this 10 billion transistor, one single transistor behaving oddly. Instead of 1, it is giving you output of 0. Whether a chip will work like that, complete functionality failure. Okay, instead of you're off, you wanted to on the phone, it will off the phone. Like that, it will behave completely different. If your phone is, let's take just example of mobile phone, or you wanted on the light, or just do not on because you're functionally failing your chip. All these are important to functionally to work properly. The code has to not to having any bugginess, and it will be written in a very long to understand better. Okay, and this is performed by the design verification team. It's called design verification team will spend 70% in chip development time while verifying this chip only. This is the logic basically. Okay. So the tools required, basically these tools required for this verification, design verifications are VCS and so from the Synopsys and Xilium from Cadence and Kestrasim from Mentor Graphics. Okay. So this is the analog layout design. So in the analog layout design, there are 2-3 sections like custom layout and of mixer signals. We have a lot of sections in the analog design. So what the analog layout people basically? So your logic isn't completely in gates, right? You can't use the gates in your chips directly, right? It has to be in a standard way of that. It has to be in a CMOS structure or what you say like any FinFET. It should be in a FinFET format, right? For that, for each and every gate, let's take if you have a flop, that has to be go to again the CMOS structure. Okay, so that will be done by the custom layout teams. They will design each and every gate in a CMOS structure, and that will be used by the physical design people. There will be no AND gate symbol or a NOT gate symbol in the physical design. Everything that will be there in a CMOS structure or a FinFET structure. Not you say anything. Okay, everything will be converted into a physical layout format, not in a circuit design, not in a Verilog format. Okay. So this will be consist of analog digital converters, digital to analog converters, op amps, adders, and clock gators, adders, substructures. All this will be converted into a CMOS structure in a custom layout. Okay. Tools used for this cadence from the cadence virtuoso, mainly used for the standard layouts and caliber to verify the this standard cells. Basically, we call it as a standard cells. Okay. Now coming to the physical design. So what the physical design? So we have the layout, we have the code in a circuit in a Verilog. You have to convert into layouts. Okay. So the gate level Verilog netlist code into geometric layout representation on a silicon. Basically, this gate level netlist will be converted into a layout representation on a silicon. Okay, we are not converting in a manually, right? We are not getting a silicon into our table and we're just not deploying that complete logics into we just that are all are in the nanotechnologies. We can't see it in our eyes also, right? So nano is like 10 to the power of 9 meters basically. Okay, it's very small that even our can't see with a microscope also, that much very small. The fabrication will be done, that much of technology is evolved now. Okay, so that is called a nanometers when you see. So even a single wire and a single connection, if you see right here, and get to OR gate, there is a connection. Even this net, is if it is not properly routed or it is not properly etched, it's gone. The chip is not will not properly. Accuracy with what we make, it has to be at physical design. The logically it has to correct design verification step, and physically it has to be routed, and it has to have a no design rule violations. Okay, for every technology we have a different design rules that are designed by the fabrication units, fabrication basically the fabrication companies like Intel and TSMCs. Okay, at this stage we'll plan all the macros to be properly placed. The macros are the RAMs or a ROMs or a analog digital converters or any kind of a logic like USB logic, and that will be properly placed. And again, we have to give each and every standard transistor and standard solar transistor power. That is called a power planning. Okay, and the placement of the cells, it should not overlap it with any of the transistors. The proper spacing should be there. Okay, and the routing is like completely the net to net connections. All these are the number of levels of each and every routing. We are currently at 25 layers, like having a billing. You can say, take example of billing, right? How many floors we have, right? For each floor there is a wiring. The same thing like that. For each floor there is a wiring. That will be like a completely insulated with each of the layer. We'll be properly routing each of the layer without any shorts. Completely it will rotate, zero short. One shot, complete burn. It will not even work. Okay, for each and every step we have to be meet properly to work a single chip. Okay, without that even a single mistake will cause a fabrication unit or an investor to lose billions of money. Okay, this is about the physical design. And coming to the fabrication is process of creating a circuit on silicon wafers. So this complete physical design thing, the layout things, will be printed out on a silicon wafers. So that are the purest semiconductors which will behave complete chip behavior. So they are involved in photolithography, doping, etching, and deposition of insulators. All this will be involved. Okay. At a time, in a single wafer, there are hundreds of chips will be printed out or what you say fabricated, and they are diced into individual chips again. Okay, so let's and that are for each hundred of chips, only 50 to 60% of the chips will work. Rest 30 will fail because of the fabrication. A small issue that caused while routing or while printing out that each of the metal layers. Okay, and next, coming to the packing and testing. Without any packing, it may get burned out or due to some external factors because of temperature. We have to be connected. We have to pack it properly, and the pins externally connected are can't be in a nano scale, right? They has to be in a again in at least a millimeter scale, right? To connect to the external input and outputs. So that are properly connected to the motherboards. Okay, and while connecting there should be no functional failures and which meet the requirements, and it should not heat. We have to take a proper techniques to pack them. So that is like a graphene or a carbon we use to pack them. Okay, sometimes we use a gold also to on the chips to properly not to melt down. Okay, and coming to the EDA tools. What are EDA tools? EDA tools are the CAD tools or the software tools that are required for all the VLSI flows, and the major standard industry tools provided by the companies like Synopsys, Cadence, and Mentor Graphics. Okay, the major all these flows have a different, and both are same in terms of the synopsis or a cadence are providing the industry all the standards required for the requirement for each of the companies. Okay. Yeah, coming to the VLSI design of front end and back end flow. What is front end and what is back end? Front end is all about code. You see, there is a no layout simply. There is no layout to see. Just you see the text in all your files. The logic RTL code will be a behavioral representation, just like a flop you will refer, right? You'll see the behavioral representation that will be converted into a coding, and that code will be implemented in a Verilog format, and that is logically verified, and then it will be synthesized properly here. Okay, all about the front end you will be working on. And what about the back end? Backend is all about a layout. You see the gate level representation. You see the circuits of the each gate in a transistor format or in a gate level formats. You will see from them. Okay, you will be verifying the each of the logic properly, getting a power inputs and everything you see in a layout format from it. You will not see any kind of a text here. You're getting loading the inputs and working out on a complete layout. Circuit design, circuit verification again, physical design, physical verification, and the closing of the block if you're successfully meeting all the requirements of the fabrication units. Okay, so this is about the front end and back end. Anyone have any questions here? If someone is asking what is AMD flow, so it's like AMD flow. Each company has different flows. I can say this is a flow, but the same this is a mastery flow. They has to follow completely the one which showing. But in terms of setting the each and every script or each and every methodology requirements for the GPU or a CPU, they set up in a formatted in an automation way. So that will be designed by the CAD engineers, what you say. That is called AMD flow. Okay, what we can say. Intel has the different flows. NVIDIA has a different flow. Qualcomm has a different flows. Everyone has a different flow. But ultimately, they will follow this rule only. Everyone has to go to this rule only. But only thing is that to integrate the inputs required for each and every step is different. I required a different inputs, and NVIDIA required a different inputs. Like everyone has a different input formats and input way they have different output formats. Then ultimately they has to give a GDS format to the fabrication to manufacture the each chip. Okay, did I answer your question? Coming to the visual representation of the each flow. So behavioral representation is like this. You can see right here the behavioral representation will be like a adder, input adder. Okay, the three input adder having a carry and output of three input, and we see that here it is represented again in gate level representation. Okay, gate level representation again is like each gate will be designed, then it will be converted into transistor level. Okay, and each transistor level again converted into layout representation by the analog layout team. Okay, and this layout of each adder or the subtractor, what you say, will be used by the physical design engineer in their layouts to functionally connect it properly and physically they will not have any issues. Okay, and coming to the global semiconductor market, so what the current trend going on, how much the valuation of the each company and how much the revenue. So this is only the revenue, it's not even a market valuation, I can say. Okay, so 600 billion revenue currently earned by the semiconductor market, like complete market is 600 billion and growing every year 20 to 30%. And India has very less percentage now. We are just investing 10 billion that is started in the current year. Okay. The program that we call as a Semicon India. Okay, focus on designing and manufacture and packing. Okay, designing we have a lot of requirements currently, and manufacturing was set up by the companies like Tata. Okay, and Micron we have the major players. I'll go to that also, and we are also part of the Indian semiconductor mission. ChipXpert is part of Indian semiconductor mission, and we're giving a complete engineering qualified people required for this VLSI. Okay, and coming to the VLSI shortage, there is a lot of shortage for the VLSI talent. So we see the very less number of people are with having a talent required for the VLSI. Still, India requires a lot of talent in manufacturing of this chip and designing this chip and packing. And support for India in a domestic semiconductor was very in a longer run actually. So currently you can see that there are a lot of issues going with the USA, China. So there's the complete sanctions on China, and there is no chips that has to use from the US, right? So that will causing the China a big loss that they can't use any of the chips other than the manufactured in China now. And 90% of the chips are manufactured in US only. Okay, so these chips, if they block in future with India also, what's the issue? Like, what's the cost? Like, what's gonna happen? So that's where that India started its own manufacturing hubs. We don't have a single manufacturing unit in India. Okay, like Intel has, TSMC has, but they have their own country providing. But India don't have any fabrication units. Micron and Tata and Foxconn Vedanta started their major investment in Indian semiconductor ecosystem. Okay, so these were the major investors in India currently, and there is a lot of requirement talent in India for the semiconductors currently. And India has providing the 70% of the workforce currently for the globally. So we are working with all the US projects. That AMD is taking out a lot of talent for the US companies, for US uh, chip manufacturing units. Okay, but India don't have any of the major companies that are providing this VLSI hub, basically the manufacturing units or a designing of this chip. Okay, in future we have a lot of requirement for this VLSI. There's no way that something can replace this AI with our workforce, because this is completely different world of analyzing and logically thinking. This is completely different, and thousands of jobs. Let's take the target of at least the 50,000 jobs are coming in this 3 years now. We have a lot of requirements. If one fab is started, for one fab at least require 30 to 45,000 members to work on for a single fab. Okay, so that's the however requirements required for the semiconductors currently. Okay, coming to the modes, currently we teach in the VLSI from the ChipXpert. So we are the emerging, and we are providing an industry-focused training approach. We help of the student to truly understand what the VLSI industry works currently. So what's going on in industry, we will teach them. Okay, so you are currently working for the ASIC chips or SOC chip. We'll teach the particular VLSI things for the particular graduates required for the VLSI requirements. Okay, so mode of training is we have online and offline. Okay, we have the both modes, and we have the tools with the different industry collaborations. So we have a collaborated with the major industry companies, and we have a cadence, some mentor graphic tools currently. Okay, and we will provide the real-time projects from 7 nm to 28 nm. So we have a collaborated way also. We have the real-time projects, and we have more than 10 projects, and we will also working with industry for more than for 3 months for a real-time projects. So this will also clear out a major requirement for industry to crack their interviews and to get into the VLSI easily. And for every module, we will having a 1 hour of daily clearing out sessions with the mentors we have in the institute. Okay, and recorded sessions. You will be having a recorded sessions for lifetime access, and also materials we provide at the lifetime access. And we'll also provide a complete tool access like a VPN access until you get placed to VLSI. If you start training into a ChipXpert VLSI training, okay. We'll also prepare you for the mock interviews and soft skills learning in terms of enhancing your talking skills or interview skills or will improve in this training. Okay. Coming to delivery modes, how we deliver our training modes. So we have the offline class training in our Hyderabad center. You can visit from Friday to Saturday. I mean, sorry, Monday to Saturday, and online sessions will be in the Zoom or Google Meet. Okay, and tool access will be provided for the online and offline both. Until you get a placement, we'll provide you. Okay, we also give assistance, complete support in terms of tool practicing until you get to placement. Okay, and you'll be having a daily assignments and lab sessions for complete practice of this, and we'll be covering from the basic level to the advanced level. We'll be covering from the basic electronics, from the passive components like resistor, capacitor, inductor usages. Then we'll go for the basic digital design things. Okay, then we'll cover up the scripting languages like T-cell scripting and shell scripting. Okay, for DB we also cover out for the Perl scripting also. Okay, so this is all about the ChipXpert Training Institute. We are providing a complete online and offline training. Okay, so we can take a questions now. Anyone have any questions? They can unmute and this can ask now. So this is the day all about the day one. So the day two we are covering about each and every topic of VLSI design flow. And day three, we will also cover about a few things that are what's going on real-time industry things. We'll also help out the students who are actually wanted to pursue in VLSI, the career opportunities in VLSI. And people who actually train into VLSI will also guide them into to place in a VLSI companies in a way that if they are already trained into VLSI. Okay. And Femtech students are there, we also guide them how to get placed into VLSI. Okay. So this is all about the day one workshop. Did I miss anything? Sorry. In precision VLSI market. Yeah. So if you have a someone is asking, yeah, expert is only having a Hyderabad currently. So it is located in Madhapur, Hyderabad currently. Okay. So it is at Madhapur near 100 feet road. Okay. And is there any openings for trained freshers in VLSI? Someone is asking the same question on the top. I'm a physical design engineer interested in opportunities only at Cadence. Okay. So let us know anything can apply. Yeah. So the primary thing you have to follow to get a into a VLSI, you have to follow each and every job post that posted by each of the company. Okay. And you have to showcase that you have a right skill. So you have to learn first of the right skill that is required for the company requirements. You have to match completely with your JD, job description. Then the shortest will goes on. The primary requirement for the VLSI is like a MTech. Okay, and people who actually train right, they have also requirement on the timely basis for each of the company. Okay, and coming to the next question, is there any openings for the trained freshers? Same thing, right? So you have to find it in a way. There is no job that we can get it in a directly, right? We have to try for the proper applying for the each of the company that are having the same, like you are into domain of DB or you domain into analog or a DFT. You have to find a proper job description in each of the every company's job career portal. Okay, so that's where that it matches with your intent profile, or else it is like whether it is matching for experience profile. You have to gather that. You have to get applied for that with the proper resume formats. Okay. And someone is asking, I'm a third year BTech student passionate about VLSI and digital design. I wanted to ask if any offers for internship opportunities students like who are eager to learn. Yeah. So we have, so if you completed third year, okay, it's great opportunity that you can start your VLSI into at summer itself. Why? Because if you once you complete your fourth year, right, there is a like you are having a your friends and everything will be like in line with you. There will be again a 3 lakh students will be in line with you. There will be more people every year adding for the opportunity in the VLSI. So as early as possible, start learning VLSI. It's not like completely, it's not out of your knowledge. If you have a basic knowledge of digital design and basic electronics, you can start your VLSI from second year itself. Okay. And once you get into fourth year, right, you can directly apply to the internships in the companies like Qualcomm, Cadence, or Intel, Microchip, or any other product companies directly. They will be shortlisting easily. You have a right skills in your resume. Okay, and the interview process will always have interview. First will be a written process, written test. Then you'll be having a first level or second level interviews. Then we'll be having some kind of HR interviews. This is the how for the intern process currently going on the trend. Written test will be the first case for the any of the freshers. They has to have a deeper knowledge of basics. Okay, because the expectation for any other companies, they'll test out not with the physical design or a design verification knowledge. They'll test out your first basic knowledge is in a right way or not. They'll test out with from the CMOS. They wanted to draw some what do you say, stick diagrams. The people are not learning all these things. They just wanted to learn VLSI. VLSI is all about starting from the CMOS to the end of digital design. Then only the VLSI will start. Without that, you can't get into VLSI that easily, I can say. Okay. And the next question I can take about, yeah, we are offering, we are offering for any of the people who attended the workshop, right? We are also offering a special discount for them. So anyone wanted to enroll for these training programs. So we have a strict, we have a very strict curriculum which will follow a 6 months course. We'll have a daily assignments and a monthly 2 tests. So once you get into all these things, we have our own companies which will recruit you directly. Okay, so we have collaborated with 3 product companies and they will be taking you directly if you're trained into VLSI of ChipXpert. Okay, now institute. Okay, so we'll be suggesting you directly profile to these companies and they'll be qualified completely because we are following that much of level curriculum which will be matching with their companies. Okay. The next thing is how we know when a company is post about internship openings. Yeah, every year, right? So the internship programs will start from the end of December only. So you have to shortlist your profile by December only. Okay. Once you shortlisted, your onboarding will start from April or June, probably. Okay. So this is how you need to check in the company portals. And most of the companies will be good on-campus placement only. The percentage of companies you wanted to find it out in a product companies are bit less. I have to say the truth because it has to be in a way it is going currently. Any companies, you take a Qualcomm or a Nvidia, that will go to direct on campus drive. Okay, so they will be taking out, and the opportunities which are there having a heavy competition. In the last week we have an Intel drive which is for the internship. So in this internship, like the 90% of the internship programs, they will take for 9 months of internship program. Once you are properly qualified for their requirements, they will make you permanent position at their company. Okay. The second option for you, other than the product companies, you'll be having a service-based companies, like service-based companies or service consultant companies, we can say, that are like Wipro or Capgemini or what do you say? These are the companies which will give a complete employment directly, but the salary rangings are different from the product companies. Okay. And someone is asking when we'll get a participation certificate. Okay, participation certificate will be get on the 3rd day. Okay, so this will be shared to the people who actually attended this 3-day workshop. Okay. Yeah. Yeah. The last question, yeah, ChipXpert provides any summer internship. Yeah, we have a summer internship program for 45 days, which is starting on April 15th. Okay, so there are a lot of university people are wanted to get internship for the summer internship program. So as the complete we have a curriculum for this 45 days curriculum. If you are interested, you can call us or you can mail us, which is provided in our mails in the mail thread. Okay.